In this lecture, I'm going to show you the code for how to create an RNN with an embedding layer so that it can take text as input rather than feature vectors as input. To be more specific, we'll assume that this text is already encoded as a sequence of integers that can be used to index an embedding. We haven't discussed how to create such sequences of integers yet, but I assume you have some idea in your mind. We'll discuss how exactly that will work in a later lecture. But for now, we'll just focus on the model itself. So let's start with the constructor. As you might expect, it's pretty similar to a regular RNN, but just with one additional embedding layer. Because we have this additional embedding layer, we'll also need additional hyperparameters. Specifically, the size of the embedding dimension, which we'll denote as d, is a hyperparameter. Do we want the word vectors to be of length 20, or length 50, or maybe length 300? This is a hyperparameter choice to be made by you. We'll also need to know the size of the vocabulary, which we'll denote as v. So why do we need to know v and d? Well, this specifies the size of the embedding matrix, which will be of shape v by d. It has v rows and d columns. Why is that? It's because each row gives us back a d-size vector corresponding to a word. This is what we discussed in the previous lecture. So in total, we have 5 different numbers that we pass into the constructor. V, which is the vocabulary size, D, which is the embedding dimension, M, which is the number of hidden units, L, which is the number of hidden layers, and K, which is the number of outputs. Then we instantiate 3 modules: the embedding module, the LSTM module, and the final linear module. We already know how the LSTM and linear layer work, so I assume this requires no further elaboration. Next, we have the forward function. In the forward function, we take in some kind of x, and then we pass it through each of our layers that we defined earlier. Since our model includes an LSTM, we know that we need to instantiate an initial hidden state h0 and an initial cell state c0. As usual, the important thing to pay attention to is shapes. First, what is the shape of x that we expect as input? Since each sentence is a sequence of word indexes, which are integers, we expect x to be an array of shape n by t containing integers. Each row is a sequence of length t, and each of the t columns contains a word index. After passing this through an embedding layer, it's going to map each word index to a d-size vector. Therefore, we get back an n by t by d tensor. We should recognize this as the usual shape that we pass through an RNN. Therefore, after this, nothing else really changes. When we pass in an n by t by d through an LSTM, we get back an array of size n by t by m. If we do a global max pool, or we simply take the final hidden state, we get back a 2D array of size n by m. Finally, after passing this through the final dense layer, we get back an array of size n by k.